Welcome to this biochemistry lecture on thermodynamics. Energy is very commonly required to initiate a chemical reaction. Commonly you have reactants, and then you have an activation energy. That's the energy required to initiate for the reaction to go from reactants to products. And notice that it's a two-way. Products then can go back to reactants, but that also they have to overcome the activation energy, and that activation energy is quite large if you have a reverse reaction. So the overall change in energy required is the delta H for a reaction. We'll talk about that in relation to other forms of energy right now. So Gibbs free energy is, by definition, is a function of enthalpy and entropy. It's a thermodynamic function. It's very useful in biochemistry, and it basically tells us how a system uses energy and what requirements it has. So enthalpy is H. It's the measure of the energy, a heat content of a system at constant pressure and temperature. Entropy, which is your delta S, is the randomness of a system. So delta G is the change in Gibbs energy. It's always less than 0 for spontaneous reactions. Delta H is the change in enthalpy, which is the heat in the system. Temperature is the temperature. It's always greater than 0. It's in Kelvin. And delta S is the change of entropy. So if it's more ordered, it's going to have a smaller delta S. In fact, it can be 0. And a less ordered is greater than 0. The change in Gibbs free energy for a reaction can be quantitatively measured, and the energy is required to do work. And it's related to, again, difference between the enthalpy and the change in the entropy. So commonly you'll see with Gibbs free energy is a measure of how spontaneous a reaction is, and this chart gives you an idea. So if you have a delta H that's less than 0, a reaction will be spontaneous if the delta S is greater than 0. It'll be spontaneous at low temperatures if the delta S is less than 0. For delta H is greater than 0, it's spontaneous at only at high temperatures, and it's not at delta S is greater than 0, and it's not spontaneous at all when delta S is lower than 0. This kind of gives you an idea of the quadrant of the energy requirements of a system in relation to enthalpy and entropy. So we have two types of reactions. We have an endergonic and an exergonic. And in biology, you'll notice that we have the activation energy. You'll notice that symbol. And we also have a delta G. And a delta G there tells us how energetically favorable or unfavorable a reaction is. In biochemistry, many molecules are endergonic, which is a reaction that is thermodynamically unfavorable. So the delta G prime naught is equal to 0. We'll talk about what that means in a little bit. But that means that we have work and energy to put into a system in order for it to work. And metabolic reactions commonly have too high of an energy barrier, the activation energy, in other words, and so it's too high, and so it's metabolically unstable. That reaction is not likely to occur. In fact, breakdown of many metabolites require energy, and they'll also give off a lot of energy. So some metabolites like ATP give off a lot of energy, and we could use that energy, and we'll talk about that later. But the important concept here is if it's energonic, okay, it's positive delta G. If it's exergonic, it's a negative delta G. And that basically tells you whether energy is required. In the situation of endergonic, the energy is absorbed. Exergonic energy is released. And often we couple these two in biochemistry. So a catalyst will reduce the activation energy without an enzyme, and it's reusable. So it's not used up. So it'll just keep sitting there, and it will keep causing this reaction to go from reactants to products. It's important to note that the reverse reaction also can occur, and a catalyst will commonly facilitate that reaction, especially in biochemistry. So a catalyst is a compound that increases the rate of a chemical reaction. Catalysts lower the activation energy of the delta G, of the activation but it does not alter delta G naught. So hopefully I said that. So the catalyst lowers the activation energy, but does not change the change in free energy of the system. Enzymatic or catalysts also accelerate under mild conditions. They're very commonly regulated. Those two other important concepts. The equivalent of a catalyst is a broad class of molecules. In biochemistry, we see enzymes as the catalyst, and they again lower the activation barrier in order the activation is required from reactants to go to products. It does not change the delta G again, and it just sits there and does its work over and over and over and over. So the activation energy is what's changed. That's it. We go from higher concentration of reactants to higher concentration of products. And again, commonly, the reverse reaction can occur as well, although it's not as energetically favorable commonly. One thing, so that's in a system in biology. Commonly, we have an equilibrium that occurs in biology where the delta G is equal to 0. And in that situation, we have what's called K equilibrium, and that's equal to the concentration of the individual products divided by the concentration of the individual reactions. So delta G prime 0 is equal to, or 0 is equal, the delta G is equal to delta G prime naught plus RT times the ln of K equilibrium. In other words, delta G is equal to negative RT ln the natural log of K equilibrium. So what are the terms here? So R is equal to, it's the natural gas constant, 8.3 joules, or 1.97 calories. T is the absolute temperature of the system, and KEQ is the equilibrium constant. Again, there's the equation for it. It's basically the products divided by the reactants. So now all of a sudden, we can use this equation, and you will see this equation on tests where we take the K equilibrium and plug it in. You take the natural log of that, and you can calculate the delta G prime 0. You will want to know this for exams. Again, the equilibrium reaction, if you want to see the equation, A plus B, there's a forward and reverse reaction, yields the product C plus D. And if we go to the K equilibrium, it's the concentration of C times the concentration of D divided by the concentration of A times the concentration of D. That's the equilibrium. When things get to an equilibrium, which is very common in biology, that's what we're looking at. And that's where you start to see the delta G naught or delta G 0. So you'll hear both of them. And that's where we're going to start to see the delta G naught is equal to the delta H naught minus the temperature times entropy, the change in entropy. So Gibbs free energy is measured in kilojoules per mole. Enthalpy is measured in kilojoules per mole. Temperature is obviously in Kelvin, and entropy is measured in joules per temperature per mole. Those are the equations and the units, important to know. Okay, that's kind of a 1,000-foot view of thermodynamics. I should say that's the quick and dirty. Let's go to the 1,000-foot or the 30,000-foot view of this. We are going to see this in multiple places, including metabolism and its two components, catabolism and anabolism. So you're going to see this when we start talking about breaking down biomolecules, and when we're talking about synthesizing biomolecules. And the important element here is ATP. ATP is the energy that drives this whole thing. And you might ask, well, why? And that's because we can couple reactions. So if we have a delta G prime or delta G that's positive, and we need to get to one that's negative, we can couple the two. And if we couple the two, they're additive. All of a sudden, we have an energetically favorable reaction. So glucose to glucose 6-phosphate is not energetically favorable. If we couple it with the energy from ATP breaking down into ADP, it all of a sudden becomes a very energetically favorable reaction. And this is what you will find with enzymes. This is what enzymes do. That will be the discussion for the next lecture. Hopefully you enjoyed this lecture. There's a lot to this. The equations, we haven't gotten over any problems, but that's really where you're going to want to focus on some of your problems. Hope you enjoyed, and I will look forward to seeing you next time.